Hello, in this video I'm gonna be talking about the problem of moving game entities in the game world. The way it's done is by using vectors, and there are many things that are done with vectors that have to do with the game kind of world, the space, but today specifically we'll be talking about movement. Here I've got a basic kind of script, and if you look at it, if I press left, then we give velocity of minus 150 multiplied by delta, so that the speed is not dependent on the frame rate. So minus 150. So if I press left, then the position is gonna be shifted to left, and if right is pressed, then it's gonna be shifted right, and same goes for up, down. And if we're not pressing anything, we just set velocity to 0, press right, everything looks normal. But when we press both, for example, up and left, look, here I go right, here I go diagonally, and it seems to be going faster, and the character actually is moving faster. And let's say we control our player with WASD. So if I press W, for example, the velocity vector looks like this. It's just vertically up, and the length of it is speed, right? So for example, there in the code example I used 150. If I press D, it goes to the right, and the length of it is also speed. If we press both W and D, the player will start to go right and up, and we can actually combine those two vectors to get the actual kind of diagonal velocity that we get. We can do that by using parallelogram law. So we just construct a parallelogram, and based on this point and this point, the origin, we construct an actual vector that we get by combining those two. And if you look closely, you can see that it's a little bit longer than those two vectors. By combining these two, we actually kind of get a bigger vector than we want. Let's find out how much bigger this diagonal velocity vector is. So the vector that goes straight right we're gonna call x, and the one that goes straight up we will call y, and the diagonal velocity vector we'll call d. And here we have a triangle, and using Pythagorean theorem we can easily calculate the length of the d vector. So the Pythagorean theorem, so the vector surrounded by two vertical lines means that it's a length of a vector. Length of vector d, the hypotenuse, equals to the length of vector x squared plus the length of vector y squared. And the length of vector x and vector y are the same. We'll just give it an alias m. And the length of the vector d, we'll just give it an alias n, and we pass it in this formula. Okay, so n squared equals m squared plus m squared, so we get 2m squared. And by taking square root from both sides of the equation, we get n equals to square root of 2 multiplied by m, and square root of 2 equals roughly to 1.41. So when the character moves diagonally, his speed is actually 1.41 times faster. But it's just a special case, really. Let's look at another situation. Here I have an entity and it follows the player. But as you can see, so for example, its movements are really kind of rough, kind of looks weird. Here is that script. If position of follower entity is bigger than x, we just kind of subtract from that position, so we make velocity minus the speed of the follower entity, and otherwise it's the positive value of speed. And similarly we do that with y position. So the actual follower entity can either go vertically or horizontally, but really what we want is for it to follow player precisely. So say the follower entity is here, follower, and the player is here. Right now the follower entity will move that way and that way, but what we actually want is for it to move that way, straight to the player. Another interesting case is if we want to support gamepads, and specifically if we want to control the character's movement by joystick. It doesn't go just left, right, up, down and diagonally. It can go actually 360, right? So we have to, for example, here is the player, and with joystick we can go that way or that way or that way or that way or that way. So, and now I'm gonna show you how to actually calculate that direction, and based on that direction the velocity. First we compute a vector by subtracting target position from the position of the entity. Basically means the x component of target position minus x component of my position, and so each component gets subtracted, and if it's in 3D then there's also gonna be a z component. So why do we need this vector? Say this is our target and this is the entity, and it wants to go towards the target. Basically what we're doing here is we are computing this vector, and we get this vector by simply subtracting this point from this point. So that's what this is, it's that vector. And actually if we calculate the length of this vector, it will be the distance between the target and the entity. Next we calculate the direction to the target, and we do that by normalizing the vector, this vector. And I'm gonna show you how to normalize vectors, but basically normalizing vectors means that it's gonna have the length of 1, and in this case the direction will be that vector, and the length of this vector is gonna be 1, and it's always gonna be 1 no matter what vector we get. So another example, here is the entity, here is the target, we subtract target position from the entity's position, here's the vec, and the direction, but the length of direction is gonna be 1. Then we calculate the velocity finally. So velocity we calculate by basically multiplying direction by speed. And speed, so the difference between velocity and speed is that speed is a scalar value. That means that it's just a measure, like it's a number, right? But velocity is a vector, and vector has length and the direction. So it has the value, but also it has the kind of direction. So for example, we want our character to move with the speed of 5. So we're gonna multiply that vector by 5. And multiplying vector by scalar value basically means that we multiply the direction x by 5 and direction y component by 5. And if it's in 3D space, then also the z component. And so, for example, this will be our velocity vector. And since the length of direction vector is 1, whatever we specify speed to be, it's gonna be the length of the velocity vector is gonna be speed that we specify. Now the normalization. How do we normalize a vector? So the normalized vector we get by dividing vector by its length. So we're dividing each component similarly to this, right? When we multiply by speed, we multiply each component of direction vector by speed. Here, similarly, we just divide each component of vector v by length of that vector. And we get this vector, which length is always gonna be 1. And we calculate the length of a vector with this formula. So basically we just square each component of a vector, then we add them all up together, and we take a square root of that sum. So now let me show you that in code. And mind you that the way we calculate vectors is doesn't depend on the programming language. So for this example I'm using C++, but it can be done in any language, and in many of them the same way. So first let's correct the behavior of the follower entity. So here we've got follower position and player position, and so the player position is the target position. Now we don't need that anymore. It can be a little bit confusing because here those positions are also vectors, but actually vector is just simply a struct. So vector2, for example, here it's simply a struct with x and y, like that. And if we look at it mathematically, the point is not a vector, so this can be a bit confusing. We could just create another struct and call it point2 for two-dimensional point, but as you can see they're just similar, so we're just gonna use a vector for both positions and actual vectors. So now we're gonna find this vector. Let's call it vec. It follows the player is its target, and the actual entity's position. This can also be represented as doing this, basically just for each component. So we subtract for each component. Now let's get the direction. Actually I'm using GLM, and it already has a special function for normalization, and if you're using a math library, in whatever language you're using, it probably also has normalization, but we're gonna implement our own normalization function. And we're gonna return vector. And let's look at the formula once again. Vector divided by the length. So also let's calculate the length. Okay, now simply return v divided by and this could be explicitly written out like so. X y, like that. So we normalize and get the direction. Now let's calculate the velocity. So direction multiplied by speed, which is gonna be 100 units, and I'm using delta to ensure that the speed is not dependent on frame rate. And then you'd probably do something like so follower position plus equals velocity. But I'm using a game engine that I'm making, and it actually does it for you kind of in a transform system. So this is what you do, but it's gonna be done elsewhere, so I'm not gonna do that. What I'm gonna do is actually give the velocity, give the transform component this velocity, since it's just a local variable. So now, as you can see, the entity, the follower entity, follows very precisely, kind of with very precise direction, the player. Look. So I went back to the original solution that we had just to compare the two. So this is the original one. You see the movement. But now that we're calculating the velocity vector properly, it's smooth and looks very nice. And direction by speed. Let's check this out. Oh, and actually it's pretty important that we ensure that the length of vector is not 0. So if, because we said if the player doesn't move, it sets it to 0. So if vector dot x doesn't equal 0, and if vector dot y doesn't equal 0, then we do this, and if it does, the velocity is gonna be 0. Oh. Yes. Okay. And as you can see now, it doesn't really look like the player goes faster. For example, here and here moves with the same speed. So here we check if the vector is not actually 0. So if because here in normalize we divide by the length of vector, and if it's both zeros, then the length is 0 and we divide by 0. And yeah, and here we also should check if vector doesn't equal 0. And if it does, velocity equals to 0, 0f, 0f. Oh, like, so that's it. Thanks for watching and bye.